yesterday we reached till the definition of path width and path decomposition. Width and path decomposition, and the question which I asked you, what is the path decomposition of a binary tree? So for example, what is the path decomposition of this tree? Okay, let's call it A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. Right? Suppose this is it. So what is the path decomposition of this graph?
You constructed bottom.
What?
Constructed bottom up. And for the leaves, the decomposition will be just one back, one vertex.
Mm-hmm.
And then for suppose you are at C, you can combine the decomposition.
Yeah, then I will get a whole. Then why is it not same as the whole graph is a path decomposition? I mean, really, yeah. What you suggested, it basically means a path decomposition which consists of all the vertices in one bag. Yes, that's the first thing. Okay. So what is his? What is he says? He say, take x equal to A, B, C. I don't know what it is. G, H, I, J. No, I'm saying this is also a path decomposition. Just put everybody in bag. Anything else? Very good. So what one good idea is that let's draw this picture. E, C, B, A. Next you put F, C, B, A. Next you put F, C, B, A. What is this? G, D, B, A. And then H, D, B, A. Okay, then what is this? It is I, right? No. Yeah, it is I. I, J. This is I, right? I, J, K. Okay. L. So let's take L, J, I, and A. Then what? M, J, I, A. Okay, fine. N, K, I, A. So from here, let's go. N, K, I, A. And remember, what was path decomposition? It was sequence of vertex set. So this is my sequence I'm defining. First one, second one, right? So this is your x1, x2, x3, x4, x5, x6, x7, and what is this? OKIA. OKIA. x8. By choice, it is definitely contains all the vertices, in fact many times. For every edge occurs in some path, and we have taken a path from leaf to root, so of course every end point of every edge is part of some bag. Now we have to talk about connectivity, that if a vertex appears, then they appears consecutively and then they just you lose them, right. So for example, let's look at here A, poor A appears A everywhere, so that's great. Let's look at B appears B, and then B is over, poor guy. C, it will appear here, C and C, right, never. So if you notice, this is, so basically what I am trying to tell you that if you had a tree, a complete binary tree of depth k, then this gives us a tree decomposition of width k, like k minus 1, right. And in fact, we will define something very soon for which this decomposition we will be able to make of width 1, right. So the similar to path, right. So what were we trying to do? How did we get to path width? We had these trees, then we had this grid like graph. From grid like graph, more or less we got the definition of path width, right. So path width is more like how path like the structure is, right. So if you looked at yesterday the grid subgrade, we had a layer 1, layer 2. So from when you went from left to right, it more or less behaved more like a path than like a tree, right? So you can think of that as a fat path, right? And graph has a small path decomposition if it is basically like a fat path, whatever that means. Okay. Now similarly, we can define a notion of fat trees, and we will see soon when I define the notion of fat trees or tree width is a tree width of trees will be 1, but tree width of a binary tree of depth k could be as bad as k. And in fact, you can prove that you cannot do better than this. So if I have a n vertex graph, I have a n vertex graph. For example, if I had a complete binary tree with depth log n, right? So path width of this graph will be log n, but the tree width of this graph will be 1, right? So path width and tree width can actually differ by a factor of log n, and that's all that they can differ by. You can always convert a tree decomposition of width, width w into a path decomposition of width w into log n. And how do you do it? So given a tree decomposition of width w, you can always make it a tree decomposition of width order w such that the depth of the tree will be like order log n, and then you just do the same thing, right? But we'll get to those things. But all I want to tell you that now you can ask a question, right? I mean, path width is a measure of how path like structure it. Now you can ask, oh, what is the path width of a click? What is a path width of a click? Right? Basically whole vertex, and you can prove you cannot do better than that. So path width can be very unbounded structure, and our objective is that we want to get a path decomposition of as small a width as possible, but sometimes combinatorially it is just not possible, right? When is that? For example, one can prove for path decomposition that this complete binary tree of depth k is a canonical lower bound providing example, means it cannot have path decomposition width less than k. We can prove this. Now we have tools to prove this. I may not go. For example, similarly, if you have a grid of size k cross k, it also has a path width of k plus 1 or k, and you cannot do better than that. In fact, you cannot do better for this tree width, which is slightly more general notion, which I'm going to define in a minute. Okay. So that was so much for the path decomposition and some properties. So let's prove a small lemma about path decomposition, and then you will see how nice it is. Let x1, x2, xr be a path decomposition of a graph G, right? Then for every j into 1 to r minus 1, it holds that I'll define what this symbol means. Define delta of, this is called boundary, I equal to 1 to j xi is contained inside xj union xj plus 1 . In other words, So there are few things which is not defined on the board. Okay, so let's just define all this terminology. Okay, so first thing what we have defined, what is the symbol this means? This is called boundary. So what does this mean? This is called boundary. So what is the meaning of this? Okay, given a graph G and A subset of Vg, okay, what is the partial of A? Is those V, first of all V is in A, okay, and there exists U in Vg minus A such that U V there exists, okay, such that V comma U is in Ag, right. So basically this is what it means. So basically you have A, okay, it consists of those vertices in A which are then neighbors outside, right. This is what is called boundary. It is a boundary of set A, meaning they have some vertex which is outside, okay. So given a set A, I can define a boundary as those vertex which are present in A which are the neighbor outside the set A, right, and there exists U in Vg minus A, those vertex there exists U in Vg minus A somewhere here. So if I have a V here, it means I have a U here, so there exists an edge between them, right. So they are really a boundary of the, so and they are denoted by delta of A. So that is one thing. So this we defined, and we define the notion of separation. What is a separation of a graph? Okay. Okay. Okay, so maybe I should define it. What is separation? Separation of G is a pair A comma B such that, what is, it is a pair A comma B such that A is a subset of Vg, B is a subset of Vg, A union B is equal to Vg, right. What is the separation of G, the pair A comma B such that A is a subset of vertex set, B is a subset of vertex set, A union B is a whole vertex set, and now there are some interesting property. What is the interesting property? The interesting property is, what is the interesting property? Is that A minus B, there are no edge between A minus B and B minus A, okay. So basically think of this way, that this covers whole graph A and B, right. So if you delete this part, then there is no edge from a vertex here to vertex here, right, and A intersection B is called separation or separator, right, what I called is called separator, and is called order of the separator, okay. So this terminology you will see quite frequently being used, right, this is how you write, okay. So now you have understood it, what it means. So what it tells us that, well, if you look at the second thing, in other words, it says that if you had these bags x1, x2, xr, and you have this xi, x, okay, you have xj, then what it tells us that, okay, you take this into one side, okay, you take the remaining into another side, okay, right, union of I equal to j this and j plus 1 into r into another side. So this constitutes your A, this constitutes your B, and what is the property we have to show? That, well, if I delete the common intersection, first of all, not, of course if I delete the common intersection from there, there is no edge from here to here, right, that's anyway true here, no, that's not true, right, okay, no, what I am trying to tell, that first of all what he says, okay, is a separator, look at this guy, right. What it tells us first of all is a separator of G with separator this. So although A is a large number of chi, right, huge chunk, what I am saying, what is its intersection? Oh well, you take the intersection of these two guys, first of all that, and if you delete this guy, then there is no edge from here to here, right. So suppose this is a common part, right. If I delete this, then there is no edge from here. This is what we need to prove this, right, and that is a property which, this is why it was making us, why all our algorithms were correct, because when we said okay we cannot do this because there is no edge going from left to right, so whatever choices you have made up until now is perfectly valid. Okay. So let us try to prove this. Okay. So what it says first of all, let x1 to xn be a tree decomposition, be a path decomposition blah, it holds that, it says if you look at this part x1 and xj, right, if you look at this part, then where is its partial, which vertex has neighbor outside, then it says basically look at the here intersection, these vertices might appear also, but just look at the intersection here xj intersection xj plus 1, these are the only, so then this partial is contained inside this set xj intersection xj plus 1. Now why it is contained not equal, because it could be that there is a vertex here but maybe there is no edge incident to it, okay, there is no edge incident to it, right. So that is not part of the partial, right, it could be part of the intersection but there may not be a vertex incident to it going outside, okay. So now how do we prove this? Suppose this is not true, suppose, so now I am going to just draw this picture slightly more ugly, so here it is, right, and here it is, okay. So suppose for a contradiction that this is not true, suppose for a contradiction this is not true, what does it implies? That I will be able to find a vertex here, right, let us call it u, with property what, with it has a neighbor outside and it has an edge, right. I can implies, this implies that exists u in let us call this union I equal to 1 to j xi, u not the element of xj intersection xj plus 1, first of all that is important, and there exists v, there exists v, there exists v in I equal to 1 to j x I equal to j plus 1 to r, and where, not in where, not in, okay fine, but is it correct, can I say but not in, otherwise what is the point, I mean this is not, then it is okay. It means what, look, u is not part of xj intersection xj plus 1, right, it means u occurs either in xj or before, right. So somewhere you might occur here but you cannot occur after xj, right, because if u occurs after then it must occur xj as well as in xj plus 1, and you remember the third property of they occur consecutively. So look at the largest index where u appears, okay, what I am saying now, okay, I am going to rub this part. Okay, this is our xj, right? Okay, let A be the largest index where u occurs. Clearly, u is less than equal to A is less than equal to j. And what can you say? And let B be the smallest index where V occurs. Where V can occur. Right? B can occur here or ahead. So I am saying look at the, so let B be the smallest index where V occurs. B must be greater than or equal to j plus 1. Okay, fine, right? So U occurs somewhere here, V occur somewhere here. Okay, so if I draw the interval containing U, it will be somewhere here, and if I take interval containing B, it could be somewhere here. What is the meaning of this if this happens? In which bag can I put the edge UB? It means, look, because U comma V is an edge, there must be a bag containing both the endpoint U and V. But what I have shown, if this condition happen, then U and V cannot be put into the same bag. Agree? So what did we prove? So we have proved that all the vertices who has a neighbor outside, right, into the first guys are actually contained inside xj intersection xi, right, right. So when I take this guy, I have shown to you that all the vertices which could have a neighbor outside is contained inside xj intersection xi. So if I delete that vertex set from my graph, there cannot be an edge from the remaining part in the left side to the remaining guy in the right side, because any guy who had, you have deleted it from the intersection. So this proves this. So once you prove this, this immediately follows. Okay.
Why is the intersection xj plus 1?
Oh, this is plus 1.
The separator is it, why is it that intersection?
It is, what do you mean by?
This is the separator, but
I never said this is a minimal separator or nothing, right? It's a separator. I am deleting more vertex maybe. So how does it? It will still separate, right? Right. So if there are two, if I delete some things and there are two people do not have edges, and I delete some more, I still this left and right will not have an edges. So that's okay. So is this fine? And this is a basic crucial property about path width, and we will prove a similar lemma about tray width. This. Okay. So done. Okay. This implies there does not exist a bag containing UV, although U comma V is an H. Agreed? Contradiction. Okay, so we have shown this. Okay, this lemma. Okay, now what I am going to do is to define a notion of canonical path decomposition, which is very useful property to have while doing a dynamic programming algorithm. Okay, so let's go from here. Okay, so let us look at a path decomposition. Okay. Is there any use if there are some two bags which are consecutive and they are same? What I mean by this, suppose x2 is equal to x3, then I make a new p prime which is x1, x2, I forget x3, I have x4, x5 and then xr. I claim if this was a correct path decomposition, even this is a correct path decomposition, right. So what is a, so this is like a kind of, what is that called, a natural path decomposition which you can define. So what does this means? So if you have a path decomposition of width p, then this sequence naturally defines a sequence of separators of size how much? P, not p plus 1, p. Why? Because two guys are not same, right. So their intersection will at least be one less, right. Right. If both of them has size, could be size p plus 1, I am not saying it, but their intersection cannot have size more than p because they are consecutively they are not same, right. So do you get it, right. And we already have seen that if you look at here, then x2 intersection x3 is a separator from left to right. You look at x4 x5, look at the intersection between them, that is a separator from left to right. So basically what I have done is I have like layer by I have put the separators of my graph exactly the way if you look at your grid, right, yesterday, right, we have deleted, right. So if you delete each column, there is nothing going from left to right, right. So basically there also each columns were like a separators which were ordered in a particular sequence. So in path decomposition also, here we can think that it is a very nice sequence of separators of order p being put in a nice way, okay. Okay, so now let me define. So now I am going to define a notion of what we call a canonical path decomposition, which is useful for designing algorithms, okay. Okay, so a path decomposition of p, a path decomposition p x1 to xr is called nice of a graph G, is called nice if first, what is this, x1 equal to xr and that is equal empty set. Secondly, for every I in 1 to r minus 1, there is a vertex w, okay, or let us say there is a vertex v not in xi, okay, such that xi plus 1 is xi union w, or there is a vertex, okay, there is a vertex w in xi such that xi plus 1 is xi minus w, okay. So what does it tells us, okay. So first of all it tells us that look, first bag is an empty set, last bag is an empty set, and in between you are doing the following operation. You are taking the previous bag and you add a new vertex to it if which is not present there. So this is what the first thing does, right? There is a vertex V not in Xi such that the Xi plus 1 is Xi union V, and this is basically called introduce node, right, because it is introducing a vertex V. Or what you can have, there is a vertex W in Xi so that Xi plus 1 has been obtained by deleting W, right. So this is like forget node, forget. So this is like a, this is called a forget operation or forget node, okay, right. Okay, so let us look at our yesterday's example and try to see if we can make such a nice path decomposition for such a graph. Okay, fine. So we had nice example yesterday, if you recall. Okay, how will we consider, right? So how you do it is that, look, this is empty bag, this is nothing, then you create A, fine, then let us introduce AB, B got introduced, right, because this union this. Next what I will do, I will introduce ABC, okay. Now let us, what will we do? Let us forget A because A is not useful anymore, because you see the current boundary, whichever you do not see, never need in future, forget it. So next I get BC, so this bag I have something from here I have forgot. Now from BC let us go back and introduce what? BCD, right, and from BCD let us go back and introduce BCDE, fine, one. So we are here. Now who all we should forget? We should forget BC, but we should forget only one at a time. So I will forget, say, BCD, and then no, what I am writing, yeah, this is fine, CDE, okay, let us write CDE. So we forgot B, and then whom do we forget? DE, so we have DE, okay. Okay, so now let us get G in, my god, okay, it is fine, DEG. So from DEG what we should do? From DEG let us forget E, right, DEG, no, we should take F first, right. So DEG F. Now we have taken DEG F, now we want to go this side. So whom should we forget first? Forget, you can forget F, G, any one of them, because you have to forget both. So first let us forget DEG, then from I forget G, so I will get what? DE, so we are still DE, then we go to DEH, we got DEH, then we will go to DEHI, oh god, oh is it correct? DE, DEH, right? There are many ways of doing it. From DE, I can go to DEH and DEH, huh? Yeah, because D is all the job of D is anyway done. You are right. So we can do, you can forget DE. So we can give EH, and from EH we should go to EHI, and from EHI let's go to HI, right? From there let's go to I, and let's from there go to empty set. So this is your sequence. Okay, tell me one thing. How long this sequence be? Can you upper bound R in this? Even now, if you notice, if two bags are same, I can merge them, nothing would happen. If two bags are exactly same, I will merge them. So in every bag, some action would have been happening. Either some vertex will be introduced or some vertex will be forgot, and it will exactly happen once for every vertex. So R is actually bounded by 2 times Vg, but we also have this and this, so this one at most, right? Because every vertex is introduced once and forgot once, and in every bag some action is happening, and exactly one action. Actually, it will be exactly equal to this actually. No? Let's see, right, how many vertex it has. 1, 2, 3, 4, 5, 6, 7, 8, 9. So by our choice, 1, 2, 3, 4, 5, 6, 7, 8, 9. Why, man? 1, 2, 3, 6, 1, 2, 5, 4, 9, 18, right? We have 19 only, right? Why? Good question, no? Empty is creating lot of empty. That's okay. In the between there is like, yes, that's a difference. So it is 2 times Vj plus 1. It doesn't matter. Why are they killing ourselves? Yes, it can be done, right, with something. Okay, that's not interesting. Okay, so what is a theorem we can show from here, that given a path decomposition, you can compute a nice path decomposition of the same width in nice time. Okay, and I'm not give a proof for that. That's like an exercise in the book, and let that be an exercise. So what does it say is, let me just at least state the theorem lemma for you people. So let me state the lemma. My God. So lemma says, if a graph G admits a path decomposition of width at most p, at most p, then it also admits a path decomposition, then it also admits a nice path decomposition say at yp, say of width p, then it also admits a nice path decomposition of width p, right. It is more cleaner then of width p, then it also, then otherwise at most. Moreover, given a path decomposition of width, or given a path decomposition p so to xr of g of width must be one can in time p square times max of r times vertex set of G, I wouldn't say of width P time computes a nice path decomposition of width P. So basically what happens is that why it is useful. So now when you try to do DP, dynamic programming algorithm, from left to right, you know that when you go from xi to xi plus 1, very limited changes has happened to the graph. Either a vertex has been added to the graph, or look, and if a vertex has been added to the graph, all the edges which are incident to it, all the edges which are incident to this newly added vertex, its neighbors must be present in the previous bag. It cannot be going somewhere else, otherwise that those two guys can never be part of some bag together, okay. So that's very interesting thing, right. So when you go from left to right, I only have few choices to consider when I am doing a dynamic programming. Either at this point of time a vertex is forgotten or a vertex is introduced. So I only have few cases to consider in my dynamic programming, and then by the previous lemma about path decomposition, we know that its intersection is a separator from left to the right, okay. So this is how, why it is useful, right. It is basically, its basic use is not to prove something very structurally, but primarily in dynamic programming algorithms, because it gives you a very nice structure to make DPs. I don't know whether I will have time to do a DP today. I only have 30 minutes left, which is good. I can be more slow now so that I can eat up my time. Who wants to do it? I will leave the DP for Rouhani, poor Rouhani. Okay. So now, so this is all I wanted to tell you about the path decomposition. We'll come back. So I'm not going to give you this proof. It's very easy. Given this, if you just play around with it, you can compute this path decomposition. It's like, okay, fine. Like I have this bag in the beginning, right? X1, like you create X1 from empty set, then add one vertex, then add one vertex, then add one vertex, then add one vertex, then you get back to X1. Now you look at X2 minus X1. Okay, either X2, whichever is forgot, whichever you have to forget, say you forget. Now whatever you have to add. So it's like I am at X1, I am at X2. Okay, so first let's see which of these elements are not present in X2. So forget. Now let's see which all guys are present in X1. So from here, add. That's it. It's all that it is. There's no more. I mean, when I left it an exercise, it's really an exercise. Okay. Fine. Now what I would like to introduce is the notion of tree decomposition. Okay. So basically it's a generalization of, so now what I would like to define is the notion of tree decomposition, and so some very beautiful thing. Okay. On tree decomposition I can waste my half an hour easily without doing a DP. So this is fine. For example, I can give you an algorithm to compute tree decomposition, for example, right, and I can kill my time. So fine, tree decomposition. So what is a tree decomposition? It's basically a generalization of path decomposition, but the way the behavior was, so remember I try to tell you that I can visualize this path decomposition as basically as two tuple, right. Path decomposition of a graph G can be visualized as a pair where P is a path and what is that called, and there is a, let's see what, okay, P and xt T in VP as a pair, a path, and xt T is in vertex set of A. So which subset where xt are subset of Vg, right. So basically you can think of I have a path, right, and each vertex in path has been assigned some bag, right. This is what it is, which satisfies the properties A, B and C. Every vertex is part of some bag, every. Now what is the definition of tree decomposition? It's basically the same thing, but I will replace path with a tree, and basically think of this where this like tree is a model, right, tree is a model. So like I am trying to model my graph as a tree. So how do I say, okay, take this tree and now I am going to assign to every vertex in the tree a subset of my vertex set which satisfy property A, B and C, right. But this tree is what is a model, and this tree on which we do our decomposition or dynamic programming and all kind of things, and it has all nice separator properties the way trees had the separator property, right. So when we were doing dynamic programming on path, what we said, okay, look at this end, then look at the graph induced on everything below. When we were doing tree decomposition, like doing a DP over tree, remember we said, oh, if we are here, then look at the subtree rooted at this. Now what is the canonical thing which you can associate? If everywhere there was a bags, then the canonical thing will be, oh, this is nothing but now it means graph induced on the union of vertices in these bags, right. The way you had path, then what is the canonical thing to consider? Look at the graph induced on all the vertices in the left of this. So here all the vertices which is part of some bags in the nodes which is induced on the subtree, that is it. Okay, but now let me formally define what tree decomposition is, right. So much about intuitions, which is a very a tree decomposition of a graph G is a pair, a tree and xt T in Vt called a bag, called this called bag that satisfy following three conditions. First, again it was that union V in Vt xt is equal to Vg for every edge u comma v in Eg that exists I such that u comma v is subset of xi, right. There is exists I in Vt such this happens, right. So basically, so just to differentiate between the graph and the tree, we will use to, we'll call the vertices of T as nodes and vertex of a graph by vertex, just to distinguish between which graph we are talking about. So whenever I say node, it means I am talking about this T, and whenever I say vertex, it means a vertex in the graph G. Okay, and what is the third property? This is again a nice connectivity property. For every u in Vg, the set Tu, what is Tu? T in Vt, okay, u is contained inside Xt, okay. Induces a connected subtree. This is basically bags that contain u. What it tells us? It tells us that look, if you look at the path decomposition, what we said, if a vertex appears here, then the vertex appears in everyone in between. So that's a path. So that's a subpath which is connected. Now I'm generalizing the same concept to a tree and say, look at all the places where a vertex appears in all the bags, and look at that. That is a subtree. So in other words, if you look at the example, okay. So for example, what it says, suppose my T is a tree, okay, this is my tree, and it has bags like some x1, x2, x3, x4, 5, 6. Done, 14. So what is the first thing? Look, if I take the union of all these vertices, it is vertex set of G. You give me an edge, then I will find a node in your tree so that both the endpoint is present there. It is exactly like a bag. For every S, there is a bag that contains both the endpoints. And what else? For every U in BG, look at which all the bags it contains. So for example, it is contained inside this bag, right? Then this is a connected subtree. It cannot happen that a vertex U is present here and then present here. Then if you look at the graph tree induced on this, it has two components. Tree induced on the vertices which contain this is not going to happen. It will always be a connected subtree, right? This is okay, but this and this not okay. This and this not okay. Okay. So this is an important connectivity property. And if it has a connectivity beautiful property, now we proved a very nice analog of, remember what we said, that the intersection is blah. So you always think of this tree as some rooted tree. You can always think of them as a rooted tree, okay. And basically what it says that now what will be the canonical way of understanding this partition or decomposition? Look, if I delete an edge, say A and B, this delete an edge A and B from tree, then tree will partition into two parts, one containing B, one containing A, okay. Let A comma B be an edge E of T, and then T A, let T minus A B be the tree after deleting the edge AB. Now let us call T A subtree containing A and T B subtree containing B, okay. So for example here, okay, here this is my A, this is my B. Now what it will tell us, that look at all the vertices here and look at all the vertices here, right. Now there is an intersection between them, right, intersection. So I can, the way I made A comma B, so what I can say, so look, let A equal to union of x j J being in vertex set of TA, and let's B be union of J in vertex set of TB X. Consider this partition A comma B. It's like not partition. Clearly, since I have only deleted edge, every vertex is part of, like union is vertex set of G. But if you look at A and B, I am going to claim to you that this is going to provide a partition where it is going to be, where is my intersection contained inside? The intersection will be contained inside this bag and this bag, right? So this, okay, this or other word I can say the way before, the delta of A is contained inside XA intersection XB, because now with respect to this edge A and B are properly well defined. So it is an XA intersection XB, right? So it is after I delete this intersection, there is no vertex from here who is jumping around here. No, it's separation. It separates things properly. Okay. So in other words, what is the lemma which you can prove? Again, the way I proved the previous lemma is the following nice lemma, and that which is equivalent to separation property of path width. Okay. And how will you prove this? Exactly the same way. Look at the topmost node where this vertex appears, look at the topmost node where the other vertex appears, and this appears separately, then which bag this edge will appear, and that's it. T in Vg dt be a 3 decomposition So till then you people think, what is a tree decomposition of a tree? I will come back. What I just told you. Equivalently, in a separation of G, and I am not going to prove this, it is same G separation with separator, not separator, XA section XB. That's it. Okay. 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 Fine. Okay. So basically this is what it is. I mean this is basically which provides a separation property, right? The way you had a separation property for trees or path width, right? Things were not jumping around, and this is what is captured in that lemma. Now let me, because I don't have much time, let me give you another definition so that the next time whoever teaches it is easier for him or her to give you a dynamic programming algorithm. Okay, so the way there's a definition of path decomposition, sorry, nice path decomposition, there is also a notion of nice tree decomposition which allows you to do dynamic programming in a proper way. Okay, so now let me define a okay. So given a tree decomposition, we will distinguish a particular vertex in R, but distinguish a vertex R in VT and call it root. Call it root. Okay, just so that we can define parent, child, ancestor relation. So think of this have a rooted tree. Right? Just make anybody root, for example. Okay, so we will always now talk about a rooted tree. So not only I'll give you tree, I'll say, oh, R is your root. Okay, so this will be called rooted tree decomposition, and this will mean a rooted tree decomposition. Okay, now what does this? What does it tells us? A rooted tree decomposition is called nice. Okay, if the following condition is satisfied, if the following holds. Okay, what is the first property? XR is equal to empty set. The root has been assigned empty set because it is exactly the same that the last bag of the path decomposition was assigned the empty set, and the procedure to get all these things will be exactly the same. Okay, okay, and XL is equal to empty set for each leaf of tree. This is like the first vertex of my path decomposition. So now I do not have one first vertex, all the leaves are like a first vertex, so I assign them. Okay, okay, and second, every non leaf node of T is one of the following types, is one of the following types. First, okay, it's called introduced node. And what is introduced node? Well, introduced node is a node T with exactly one child T prime, exactly one child T prime, such that xt is equal to xt prime union V for some vertex V not in xt. We say that V is introduced at T. Okay? Okay. So the canonically we also have forget node, right? Okay, it's again a node with exactly one child, t prime, such that xt equal to xt prime minus some w for some vertex w in xt prime. And what we say? We say w is forgotten at t. And finally, we have join node. Okay, what is join node? A node T with children T1, comma T2, such that x of t is equal to x of T1 equal to x of T2. That's it. Okay, this is called nice. So basically, what it says is that look, if a vertex is introduced, then it's like it has only one child. If a vertex is forgot, it has only one child. And when I have a join node, it means I have two guys, and it's like, okay, same guy, and the same bag. Now, remember in the path decomposition, we were saying that, okay, adjacent people may not have the same bag or something. We cannot guarantee these things. But it is very useful property to have when we are doing dynamic programming algorithm, right? So, and again, you can prove a lemma which says that given a nice tree decomposition, okay, given a tree decomposition, you can compute a nice tree decomposition nicely. In again, what will be the idea? You are given a tree decomposition, look at a leaf, forget one each, go to the empty set, look at its the next node, introduce, then or first forget and then introduce, you get something, and then right, and then it's a tree, so you have to be careful now because you also have to make it binary, because what does it says? That every node which is join node has exactly two child. So there you might have to introduce some dummy people so that you decrease the, what is that called? So you could have a tree decomposition where this tree is arbitrary, right? It has arbitrary number of children. So like you have to like keep this subtree and then one, and then make another guy, and like popping up so that it becomes a sub. The way we generally make binary trees out of things. Okay. So what did we learn? So I still have 4 minutes. Okay. So what is the tree decomposition of a tree? Huh? Kire? Basically take the tree itself as T, and from the leaf just keep for every edge, for every vertex, look at its parent and just add that as a bag, so it's like 2. Okay. So if I give you a feedback vertex set, if a graph G has a feedback vertex set of size k, what is its tree decomposition? If a graph G has a feedback vertex set of size k, then what is its tree decomposition? If a graph G has a feedback vertex set of size k, delete that set X, you will get a forest, right? Think of them as a tree, right? Just so you have a tree decomposition. Now look at the set X, go and add it to every bag. So you got a tree decomposition of width basically k plus 1. Now if you had a very good algorithm over graphs of bounded tree with like some C power tree width kind of algorithm, then this will also use a C power k algorithm to find a feedback vertex set in an unwrapped data. Right? So this is how people in parametric complexity use tree width. Right? So what we say that look if my problem is like, okay, if it has a solution, then the tree width of the given graph shouldn't be too large, because if it is too large, then I will be able to answer this question in either yes or no in polynomial time or in c power k time. Otherwise, the tree width of this graph is small, and then there's an algorithms to compute this tree width. I mean, or the proof which you get itself will give you such an algorithm, and then you apply the tree decomposition algorithm or dynamic programming algorithm over this tree decomposition to get the desired algorithm. So this is how actually we use. It's not that. So it's basically we relate the structural property of how the graph can be decomposed with the property or with the problem which we are trying to solve, right? And then we combine these two things together to get the desired effect. Okay. So, for example, vertex cover. What is the tree width of a vertex cover? If a graph has a vertex cover of size k, right, then I claim that it has a path width of size k plus 1. Again, if you delete this, it's an independent set, right? Just add this guy to everybody. So it has a path decomposition of width k. So that also gives an algorithm of 3 power k basically be computed, a path decomposition. So that's a 3 power k algorithm. And things like so forth, and right. And so actually for vertex cover or parameterized by independent set, parameterized by tree width, you can give an algorithm with running time 2 to the power tree width, which you will see in the next class probably. But you cannot do better than 2 power tree width unless you can solve SAT without any this better than 2 power n, where n is a number of variables. Okay. So since I'm supposed to close the lecture today early, so I close my lecture because it's not that I can do a DP over graphs of bounded tree width for independent set itself in 10 minutes. That's practically not possible. So bye class, whichever that class is. See, I gave you 10 minutes extra.
Thank you, sir.